All right. Hey again, Honors Chemistry. So now I am on page 9 of the notes that start on this page. We last talked about the need and the for equations to calculate energy with respect to mass and change in temperature or no change in temperature at all. And so now we're going to talk about how I can use these equations and do some calculations. So this is big calculations help. So before we get into calculations, there are going to be some unit conversions that we have to keep in mind. Mass in grams or kilograms. Don't forget that 1,000 grams is 1 kilogram, or 1 kilogram is 1,000 grams. The way that you remember seeing it is 10 to the third gram is 1 kilogram, or 1 kilogram is 10 to the third gram. Okay? For our calculations, we need to use grams for our calculations. Why? C and H are in units of gram. So C is in joules per gram degree Celsius, H is in joules per gram. So we need grams. So if I need to convert, and I'm going to do it over here, if I'm given kilograms, don't forget how to do dimensional analysis. I'm going to have kilograms on the bottom and grams on top. That means I have to use this. I multiply by 10 to the third over 1. If the question ever asks you for kilograms, I start with grams. Later on, I'll do 1 kilogram over 10 to the third gram. I'll divide by 1,000, and that will give me kilograms. So if I ever have kilograms on a problem, so let's say, and I'm going to do it quickly, let's say I told you I had 50 kilograms. If I had 50 kilograms for an energy calculations problem, I need it in grams. So I'm going to multiply that number by 1,000 or 10 to the third. So 10 to the third grams over 1 kilogram. Kilogram will cancel out, and I will get 50,000 grams. Okay? Same idea. Another unit conversion to worry about is joules or kilojoules. And I'm just going to write it as 10 to the third joule is 1 kilojoule, or 1 kilojoule is 10 to the third joule. Okay? And I'm going to say this again. We need to use joules for calculations. And so let's say I told you I had 60.6 kilojoules, and I did something like that, and I wanted you to use the kilojoules for a calculation. If I had 60.6 kilojoules and I want to convert that to joules, I would multiply by 1,000 or 10 to the third. 10 to the third joule over 1 kilojoule is going to be equal to 60,600 joules. Or what if I wanted you to convert to joules? This is going to be big, kilojoules. What if I was like, oh, express your answer in kilojoules? That's later. We're going to use joules in the calculation, but later on, what if I wanted you to express it in kilojoules? Well, let's say I got 155,500 joules. If I want that in kilojoules, if I do dimensional analysis, joules goes on the bottom, kilojoules goes on top. 1 kilojoule over 10 to the third joule. Basically, I'm dividing by 1,000. And so if I divide by 1,000, I'll get 155.5. These two zeros were not significant, so I'll just say kilojoule. Okay? So keep that in mind that we are going to have some energy conversions. We're going to keep it in the 1,000. So 1,000 gram is 1 kilogram. 1,000 joule is 1 kilojoule. If there's any other conversion, if I do like a megajoules or something like that, you might see megajoules, MJ, which is a megajoule. That's 10 to the 6th joule. So I would have 1 megajoule over 10 to the 6th joule, or 10 to the 6 joule over 1 megajoule. All right, I might have that later where we're doing the same type of conversion. Let's get straight into doing calculations now. All right, so don't forget that we have two equations. We have Q equals MC delta T, and we have Q equals MH. I specifically planned these two equations to show you how to plug and chug. So example 1, we're going to be changing temperature. So it says a 12-ounce can of warm soda at 42 degrees Celsius is poured onto a cold block. Over time, the soda that was poured onto the rock began to cool to 10 degrees Celsius. So I have 12 ounces of warm soda, 42 degrees Celsius, and it cools to 10 degrees Celsius. Assuming the heat capacity of the soda is the same as the water, all right, so soda is a liquid, right? Pop or soda is a liquid, so I have liquid, and it's 12 ounces of it, which I wrote over here is 340 grams. The liquid is going from 42 to 10. Assuming the heat capacity of the soda is the same as water, how much energy is released from the soda in joules? Well, I have a temperature change, temp change, so I know that I need to use Q equals MC delta T. I didn't say anything about a phase change. I didn't know, or I didn't go through any of the freezing points, melting points, or boiling points of water. So I'm just going to be using Q equals MC delta T. Okay? So I also don't want you to forget LOL diagrams. So the way that this LOL diagram would look, right, I'm just doing LOL. If I had warm soda, I would say that I have like maybe 3 or 4 bars of thermal energy. And then if it's soda, I'd probably have 2 bars of liquid phase energy. Okay, I'm just like quickly sketching it. And then if it's warm soda and it cools down, it's still going to be soda, so it's going to be the same phase energy. It's just probably going to be cooler. So thermal is just going to be cooler, and then it's still a liquid. So thermal energy is going to be lower, phase energy is going to be the same, and this soda is going to be losing some energy. So this is kind of quickly like thrown over here, but if I were, don't forget that I could first qualitatively talk about energy being gained or lost in the system. So make sure you have practice in doing LOL diagrams, because that's part of worksheets 1 and 2. But overall, I'm going to have less thermal energy in the system. So this Q is going to be Q of thermal. All right, so now let's go into plugging and chugging. M is mass in grams, and it said it was a 12-ounce can of soda, but I told you that 12 ounces was 340 grams. So I have 340 grams. C, I said, assume the heat capacity of the soda is the same as water. And this is liquid. We know that soda is a drink, so it's a liquid. So if I look back at my notes on page 8, the specific heat capacity of liquid water, and we're going to use this number a lot, is 4.18 joules per grams degree Celsius. So C is 4.18 joules per grams degree Celsius. And then delta T is T final minus T initial. Okay. It says it goes from, or it's at 42 degrees Celsius, and it's going to 10. So it starts here and ends here. So my final temperature is 10 degrees Celsius, and my initial temperature is 42. This is going to be negative 32 degrees Celsius. Remember I said this in the previous video notes. Delta T is negative for cooling. So I'm going to be losing energy. Now I have my variables to plug and chug into Q equals MC delta T. Q equals MC delta T. M is mass, which is 340 grams. C is 4.18 joules per grams degrees Celsius. Notice how I just write it in as units, and I'll show you how these units will cancel out. Delta T is negative 32 degrees Celsius. Now, when I'm going and doing these calculations, this unit for C is going to end up canceling out and leaving me with J. So I have grams on top here, grams on the bottom. Those two are canceling out. I have degrees Celsius on top. I have degrees Celsius on bottom. Those two are going to be canceling out, and I'm going to be left with joules. That's what this is. These are just units. And so if I go and do this calculation now, and I'm just going to plug and chug this into my calculator, I have 340 times 4.18 times negative 32. And I get negative 445,478.4 joules. Negative. Or you could say, or 45,478.4 joules was lost. These two things mean the same thing. If I write negative, you're telling me that I'm losing energy. Or if you write the number as positive and say this much energy was lost, you're good. Okay? Now let's do a calculation involving a phase change. So it says a 12-ounce can of soda freezes at its freezing point. Assuming the phase energy of the soda is the same as water, how much energy is released from the soda in joules? 12 ounces is 340 grams. Now, I'm going to make a note here, and I'm going to move this up. If a phase change occurs, you have to assume it reached its phase change temperature. So notice how I said, oh, it freezes at its freezing point. I didn't give you a temperature. Did not give a temperature. That's because if I tell you something's freezing or boiling or melting or condensing, you have to assume it's at its freezing point. If it's the same as water, this is happening at 0 degrees Celsius and it's not changing temperature. Don't forget about the heating curve or cooling curve. Let's do a cooling curve. It's going to look something like this. Right? So we're right here in the cooling curve where it's flat. So if I want to do a calculation where delta T is equal to 0, there's no temperature change, I have to use Q is equal to MH, where M is the H of freezing. So I already told you that the mass was 340 grams. And H of freezing, I'm going to have to look back on a previous page. H of freezing is going to be, and I wrote it down here, H of freezing is going to be negative 334 joules per gram. Overall, to freeze and melt, it requires 334 joules per gram. But if I'm freezing, I need to remove that energy. So H of freezing is going to be equal to negative 334 joules per gram. And so now all I'm doing is plugging this into the equation. Q is equal to M is 340 grams. H is negative 334 joules per gram. Notice how there's no temperature whatsoever in this calculation. 340 times negative 334 joules per gram. Grams ends up canceling out, and I get this big number, negative 113,560. Negative 113,560 joules. Or you could say 113,560 joules was released. These two mean the same thing. Negative is going to tell me something is released, or I could tell you that it's released. Okay? We won't worry about significant figures for right now, but they will come in later if I wanted to. This has 2 sig figs. This has 3 sig figs. My answer should be in 2 sig figs, so I would be at a negative 110,000 joules. That's 2 sig figs. Okay? All right, I'm going to end this video here. With our video notes, we did 2 basic examples. In my next video, which you could watch and the rest at the same time, or you could wait and sit to do worksheet 3. In my next video, I'm going to do examples 3 and 4 and 5, which are a bit more challenging and require some things to occur. So you could watch that before you do worksheet number 3.